Díaz, the candidate at the Raymond Labs, worked with Peter Sturm. Oh, sorry. Okay. Let's start with our motivation. Maybe some of you recognize these paintings. They are part of Monet's work. He painted Rome's cathedral under different moments, showing how objects' appearance and perception of the world change drastically depending on the illumination. Additionally, appearance is also dependent on observer, source of material, and object's geometry. Bringing Monet's painting to our days, where the use of digital cameras is present everywhere, if we select an outdoor scene, between the thousands of photos that we can download from internet, we can find a wide range of appearances that we can see in all the images. Also, recent work on photo collection has allowed to exploit image collections to, for example, create 3D geometric models of common places. These methods use mainly robust implementation of structure formulation algorithms and bundle adjustment. So with this motivation in mind, our goal is to exploit the richness of appearance to extract photometric information about the scene and the cameras. Okay, to explain how we reach this goal, first we are going to explore some of the previous work related to our algorithm. In second place, I'll explain our algorithm. I'll show you some results, and finally I'm going to present some of conclusions extracted from this work, and I'll try to answer your questions. Between the projects that have worked out in similar problems, the paper called Radiometric of multiple images used a 3D model acquired under controlled conditions to find out a directional light source and the Lambertian albedo corresponding to the objects in the scene. Assuming in this work, the authors assume a linear model for the camera radiometric function. Well, their images were captured using a well-defined setup of cameras on lab conditions. Other work that is very popular in 2007, the seminal work of phototourism shows that it's possible to make a 3D spar reconstruction and to find camera pose using image collections. And this work in 2009, a group of researchers used also image collection to estimate surface reflectance properties along with illumination. In their approach, the illumination and the BRDF were modeled in a frequency framework, and parameters were estimated using a traditional nonlinear optimization. To calculate image irradiance from pixel brightness, they used a gamma correction curve with a fixed value for the gamma term, which is not the best for images downloaded from internet. On the side of radiometric calibration, we can classify the approaches into groups. The methods that require a physical interaction with the scene, we call this the active methods. For example, when we include a color chart on the scene, or taking multiple images with different exposure and then computing the CRF, the camera radiometric function. And we can find also a second kind of methods that include those ones that exploit image analysis techniques to infer the radiometric response. For example, the work of Lin and his colleagues, 2004 and 2005, and they use specific regions of the image where color changes drastically to estimate the radiometric response. There are other works that also use noise distribution and probabilistic approaches for the same purpose. But what is exactly the radiometric calibration? Well, in a few words, it's the process of mapping the image irradiance to the intensity values. We define the image irradiance as the amount of incoming light reaching the sensor. This is in turn the result of an interplay between light and surface properties, including the geometry of the surface. Then, assuming a distant directional light source and a surface with Lambertian reflection, the image formation can be expressed in the following form, where E corresponds to the image irradiance, rho to the albedo, and L to the light, parameterized in this case by two angles with respect to the normal of the surface. Under these assumptions, this equation can be simplified by a closed form, as we can see here, where the illumination is represented by the directional light source plus an ambient term, and the direction of this light is parameterized by the elevation angle, the azimuthal angle, and the ambience term. So for a surface element J, in this case, projected on the camera I, his irradiance is defined as follows. We can see the definition for the irradiance. Given that we know the 3D model, we will mark in red circles the unknown parameters. So we can express all the terms between the parentheses like capital L, the vector for the light. Then the image intensity is the value estimated by the function f. In this case, the function f corresponds to the camera radiometric function. Expressed has a linear combination of basis and some coefficients. We extract this model of the basis for the camera response function from the empirical model proposed by Grosberg and Naya in 2004. Okay, finally, we can formulate our problem in an optimization framework where the estimated value is multiplied by a visibility constant, Vij. Okay, to explain in a better way our idea, let's explore the two image case. We are going to propose a linear solution for this case. In this case, the albedo for one particular surface element must be the same in both images. However, the colors projected on the images are not. Following our image formation model, albedo can be expressed as the ratio between the image irradiance and the dot product of the normal and the light. Given Gi, the inverse camera response function that can be also modeled as a linear basis with some coefficients, we try to find the coefficient x and the vectors L that make both sides of the equation equal values. In this case, we are also assuming that the spectral distribution for both cameras are similar. Okay, we circle the unknown values. Gathering all visible points in both images, we can form a linear system of equations with respect to the variables enclosed by the red circles. In this case, L2, X1, L2, L1, and X2, L1. Once we find the unknowns, the computation of X1 and X2 is trivial. But of course, a linear solution suffers of problems with noise and outliers present in real-world images. A nonlinear solution is also proposed, where the estimated intensity is described by two vectors, in this case, the vector A and the vector B. The vector A contain the CRF coefficients and the illumination components, and the vector B describe one albedo per point and per channel. To avoid errors due to outliers, we implement our optimization as an IRLS algorithm. So if we have 100 images, for example, and a 3D model composed by 20,000 points, you can imagine the size of the optimization problem. To make it doable, our implementation uses sparse structure of the Jacobian that allows to save memory and processing time. This is more or less the structure following the vectors A and the vector B that we mentioned in the slide before. Okay. For testing purposes, we compiled two databases of outdoor images. The first one is composed by 120 outdoor images, 5 different cameras, and for the estimation, we use 21,000 surface elements and around 65,000 parameters to estimate in this case. Here we can see the first database, some samples, and the 3D reconstructed model. For testing our results, we have a major problem because camera manufacturers rarely provide technical information about the radiometric function. So for the first database, we decided to include in some shots a color chart to calibrate our cameras. We also, when possible, we also took multiple exposure images, keeping the scene as static as possible, and that it's a hard work when we are talking about outdoor scenes, because this kind of scenes change very quickly. There are, for example, clouds, shadows, and reflections that can change very quickly. For the second database, this database is composed by images downloaded from internet. We didn't have access to the scene in this case. For the reconstruction, we use 928 outdoor images. For the estimation, we use 100 images and about 21,000 surface elements. In this case, the number of parameters to estimate are 66,000. These are some samples for the second database and the 3D model. And here are our results. We show some of our results. This is the inverse camera radiometric function for one image, estimated by our algorithm, and we plot also the results for the lean algorithm for the color chart. We have some points that represent the samples for the color chart. We fit a curve to these samples. We show results for the HDR software and also for the gross bar method. Some additional results. Well, most of the cases our estimation is very close to the samples. For example, for the multiple exposure case, in the case of the gross bar method, there are some curves that are not very good curves. We think that this is because in the case of multiple exposure methods, the images are not completely aligned, and there are some problems with the clouds, for example. Okay, for the second database, given that we didn't have access to the scene during the acquisition time, we have only comparison with Lin's algorithm, and in most of the cases, we are very close to these results. Okay, some additional results. This is some work that we are currently doing. We show at the top of the we show at the top of the slide the original images, and at the bottom we show the 3D reconstruction projected on the original images with the CRF, with the estimated CRF, and with the illumination and the albedo estimated. So in most of the cases are images that correspond, are very similar to the original images. So results are promising. Okay, some conclusion. We have proposed an approach to recover the camera radiometric calibration using a set of images. Compared to other methods, our approach doesn't require aligned images or direct access to the scene. Moreover, our method is completely automatic and doesn't require supervision or manual tuning of parameters. We believe that our results can be useful in a joint estimation of surface reflectance, illumination, and radiometric calibration using more complex models, for example, for the BRDF. For instance, using spherical harmonics for illumination. We haven't tested the performance of our algorithms without the prior on the CRF, but we would like to do it. This can be useful to determine if better models for the CRF can be proposed. This is an idea because, well, the model for the CRF that we are using is a model that was proposed in 2004, and we have seen this morning that modern cameras are very different from cameras in 2004. So we think that a more accurate model can be proposed. Okay, that's all. You can go to the web page if you are interested in the data sets, 3D models, geometrical calibration, and images. That's it. Thank you very much.
Depending if you go to an sRGB or an Adobe RGB, we have a different processing in the camera. So how are you going to account for these, or local tone mapping would be another example. So how are you going to account for this?
Yeah, well, first of all, I'm sure if the model proposed by Grosberg and his colleague, I think that they use some digital cameras in the model. What they do is they gather like 200 cameras, and they calculate the camera response function for these 200 cameras. Between these 200 cameras, I think that half of the cameras are digital cameras that include image processing algorithms. I don't know exactly how they get these camera response function. And what they do is they compute a PCA algorithm in this set of 200 camera response functions, and they extract the principal components that can model all the space of camera response functions. So, to be short, I don't know really if the model that we are using can model the image processing or not. I could say that it does, it processes this algorithm. But as I said at the end of the presentation, I think that we need, or the community needs, a better model to model this camera function using modern cameras. I think that it's a work that must be done in the next few years.
Other questions? I had one question. So I think you assume that the spectral response of the cameras is all similar. Do you have a sense of how that, if there's a difference between the response of the color gels, how that would affect?
Yeah. Yeah, we are assuming that the spectral distribution of the cameras is similar. We really don't have an insight about how different it could be. Even with this, in this case, the problem is enough complex, and to add an spectral term to the model could be very expensive in the processing time. But yeah, I'm sure that that maybe modern cameras have different spectral distribution. This could be a problem for the approach.
Well, if there are no other questions, that concludes the session. Let's thank our speaker and all of our speakers. Before we release you for coffee, we want to do a quick poll for CVPR or for ICCP next year. Go ahead, go. So
yeah, so it's not really a poll, but it's food for thought while we're eating or drinking. We need to decide on the deadline for submission, and we would like to get your input. Either send us email or talk to us right now. I mean, there will be a CVPR deadline, there will be a SIGGRAPH deadline, and we want to know what is your concept of when is it too close to the other deadlines? Should it be before the other deadlines, after the other deadlines, etc. So relative to the season that we had this year, what are your recommendations? So please contact us about these things.